So, I've seen a lot of folks are getting their two-dimensional physics work done and turned in. The Star Wars problem seemed to go well. This homework seemed to be a bit more of a challenge, which I expected. I had a lot more people ask me for help yesterday, so that's great, and we had a lot of successes. So, I know that last problem, number 4, was really, really difficult. It's probably, mathematically speaking, the most challenging problem of the semester, and so this video is going to walk us through how to do that. And then when we eventually get to whatever form of quiz we get to, there will be one problem like this one on the quiz, but it'll be broken up into pieces. So rather than just being like, here you go, here's the whole problem, instead it's going to be like A, B, C, D, E, F kind of problem where I kind of give you hints and walk you through it step by step. So as long as you pay attention to this walkthrough, you take it seriously, take some good notes, then you should be just fine on that problem. So we're going to jump right into it. This problem here, Mr. Billman there, he's dragging the box across the floor and it's accelerating. So we've been doing a lot of constant speed problems lately. We're at one now where we've got an acceleration. So mass times acceleration isn't just 0 anymore. We're going to have to factor that in. The box has a mass of 62 kilograms, and the angle is at an angle of 30 degrees. So we got to calculate the force right here, this force that he's using to pull the box. So up to this point, I've always given you that force. I've given you that angled force, and we've used sine or cosine to turn it into an x or a y force. But now we don't know what that pull force is. So that's why this particular problem is so complicated. So if we don't know what the angle force is and we need to figure that out, that's when you go into this problem kind of mode here where you need to use the x and the y direction. That's really the tricky part of this problem. You need to use both x and y to solve it. Up to now, we've either used x or y to solve most of our problems, unless it's been like a coefficient of friction kind of thing where we needed to find force normal and then force friction. That's really the only way we've combined x and y so far. This problem here, when we have that angled force, obviously that angled force has some x to it, has some y to it. We're going to need to use x and y together to solve this problem. It's kind of irritating, but that's the way it is. There's actually many perfectly acceptable approaches to this problem. The answer key that I sent you when you completed your first attempt of the homework actually is slightly different approach than the way this PowerPoint walks through it. I just made those at different times, and I just went about them differently. They both get pretty much the same answer. Due to some rounding, they're about 1 Newton off, but that's just because of some rounding that happened along the way. Both approaches are perfectly valid. And then there's a third approach, which I'm not going to get into this semester because I'm not there to teach it to you, where you can actually use the Pythagorean theorem to solve it. But we're not going to worry about that. We're just going to use the algebraic method here to solve these problems. Oh yeah, that's something I put in there the first year we did this one. So step 1 is always the free body diagram. And just in case, I'm going to pause here for about 20 seconds so you can at least think it through in your head if you haven't done the homework yet. Hopefully you've already done this. All right, so we've got 4 forces involved. Just going to put them all up here now. So the weight from gravity, always have a weight from gravity when we're on the planet. We've got friction trying to slow us down. got the normal force from the floor that keeps the box from just falling through the floor, and then the pull force at a 30-degree angle. That arrow wasn't very accurate, but got that pull force at an angle there. So the only force we need to split up is pull. The other three are already X or Y forces entirely. They're not at angles. That pull force is at an angle, so we need to split it into pull X and pull Y, which you can see we've done over here, pull X and pull Y, and those came from this pull force over here at an angle. We split it into the X and Y portion. So there's our XY diagram over there on the left-hand side. We've got all the forces we need, and they're all X or Y. There's no more angles, which is good. We don't really like dealing with angles. And also you can see down here in the very bottom left, I've got this little X and Y chart here with arrows. That shows which ways are positive. We are showing that up is positive in the Y direction and to the right is positive in the X direction. So a little diagram like that, it sets your positive and negative vectors. So now anytime we've got a positive, we know it's going to the right or it's going up. Anytime a negative vector, we know that it's going to the left or it's going down. So next up is Newton's second law. Once you have your XY diagram and you have everything kind of organized, it's time to start doing the numbers. Newton's second law is the way we do that. F equals ma. In this case, we're in the X direction first. And you can start with either direction. We're going to need both of them. That's the only way to solve for an angled vector like this. You need to know its X and its Y pieces. I'm just going to start with X. You can start with Y if you want to. So in the X direction, we've got that force equals mass times acceleration. And in the X direction, when you look up here in the problem, nope, that's not right. When you look up here in the problem, we know that acceleration in the X direction is 0.4 meters per second squared. It's not 0 anymore. We're used to a constant speed. We don't have a constant speed anymore. So here's how we deal with that. Just plug it in. We've got mass times acceleration. Usually that's 0. In this case, it's not 0. It's mass times acceleration, 62 kilograms times 0.4 meters per second squared. So 24.8 newtons. So all that means is this pull force down here, pull X, that pull force in the X direction has to be 24.8 newtons larger than that friction force. Because it's not just canceling out friction anymore. I don't really like that red. You can see that there. It's not just canceling out friction anymore. It is now overcoming friction with some additional force. So it's not constant speed, it's actually accelerating with that extra additional force. So mathematically that looks like this. So net force, again, just adds up all of the forces in the X direction. So to find force net X, we just need to add up all of our positive and negative forces in the X. So that looks like this. Our positive force in the X direction is pull X. It's pulling the box to the right. Our negative force in the X direction, which we represent with that subtraction problem, is friction, trying to slow that box down. And that equals 24.8. That equals mass times acceleration. So in the past, in previous problems, that had equaled 0 because we'd been at constant speed. In this case, it does not equal 0 because we are no longer at a constant speed. So it equals mass times acceleration. That's where that 24.8 comes from. It's a little annoying. It just throws an extra number in that we have to deal with. So we just need to keep track of it as we do our math. So what's the goal here? Why are we doing all of this? We're doing all of this because we just need to try and solve for pull. Right now, we have pull X, but once we have pull X, we can use sines or cosines to turn an X portion or a Y portion of something into the angled force, right? We can use sines and cosines to go from the hypotenuse to the x or y. So we can do it in reverse. We can use sines and cosines to go from the x or y back to the hypotenuse. And that's what we're trying to do here. We're trying to solve for pull x, pull y, anything that has pull in it, we're trying to solve for that. So that way we can figure out the total pull force. This one up here, I'm going to go ahead and highlight it just so we remember what it is we're trying to do. That vector right there. That's what we want. We got to figure that one out. To do that, we can get pull x, pull y. We're trying to get anything with pull in it. So we've got that here. We've got a pull. Let's try to solve for that. First off, in the x direction, do we want sine or cosine? I'm going to draw that triangle again there a little larger. We've got pull, our hypotenuse. I'm running out of colors, let's make that blue. Here's pull. There's our hypotenuse. Is the x adjacent to that angle here, our angle here? Yes, it is. The x direction is touching that angle. That's adjacent. Therefore, cosine, right? That's what that represents, the CAH, the CA part. That lets you know that cosine goes with adjacent, CA. So cosine goes with adjacent right here. So we know we need cosine. Pull x is the cosine portion of pull. So to get from pull to pull x, again, I'm just going to move that equation down there. Pull x is just pull times cosine. If you take the total pull here, this total pull, take that. That looks terrible. Sorry, I'm getting a little OCD here, but that's all right. And it's slightly better. You take that and you multiply it by cosine of the angle. That'll get you the x portion, which is what we want. So pull times cosine is the same thing as pull x. It's the pull in the x direction. Friction, we know the equation for that. Friction is just coefficient times force normal. That hasn't changed. And then that's true with gravity as well. Gravity is just mass times gravity. So those forces that we have equations for, those equations are still true. Friction is just coefficient times force normal. Weight or gravity is just mass times gravity. That's still true. Normal force, remember, doesn't actually have an equation. That's why we have to do all this nonsense, because normal force is just the leftover force. It doesn't have its own equation. But the forces that have equations, those forces are going to always have those equations. So friction is mu times force normal. That we can always count on that. So we're just going to plug that in there. So now we have pull. Remember, pull was our goal. That kind of rhymes. Pull is the goal. So we can solve for that now, right? We've got a pull finally after all of this trigonometry, drawing triangles, doing math, positives, negatives. After all of this, we should be able to solve for pull, it looks like. Here's the problem, though, unfortunately, is that we don't have enough information to solve for pull as it stands right now because we don't know force normal. Like I just said, there's no equation to find force normal. Force normal is just a leftover force. Once you find all the other forces, force normal is just what's left over to keep the box from falling through the ground. Well, we don't know all the other forces. We don't know pull y. We don't know pull x. Pull x doesn't really matter because it's in the x direction. It doesn't impact force normal. But still, we don't know pull y. Therefore, we can't figure out force normal yet. So because we have this, I'm going to use the ugly red highlighter this time because we don't know it. Because we don't know force normal here, we can't solve this problem yet. I'm going to circle it in red because that red highlighter just makes it too hard to read. Because we don't know force normal, we can't solve this problem yet. Here's the thing in math. This is going to come up all the time in chemistry, physics, engineering, math, any STEM field you go into, you're going to be solving things with equations. So when you are using equations like this, we've got this mathematical equation here, we're trying to solve for something with it. For everything you don't know, you need an equation to solve for it. So right now we only have one equation to work with. We've got this equation right here. We've done a lot of math with it, but it's all just based around this one equation right here. F equals ma in the x direction. That's all we've got. But we have two things we don't know. We don't know pull, right? We don't know pull here, and we don't know force normal. So there's two things we don't know. We only have one equation. That's not going to cut it. We need another equation to solve this problem. That's why this is so tricky, is because up until now, you've only needed one equation to solve for everything. That's not necessarily true, actually. Some of the times in kinematics equations, we had the same issue, right? Where we had to find acceleration, or we had to find initial velocity before we could find something else. That was one of our tricks. Remember that you had to find acceleration and initial velocity before you can find anything else. So this is kind of the same way here when you're working with forces, because normal force shows up in both equations, because it's here in the y direction. Obviously, it's a y direction force, but it's also part of the friction equation. Because of that, you pretty much always have to find normal force if you have an angled force like this, right? If we don't have an angled force, if we're just looking at x or y, usually you can get away with just looking at one or the other. But when you're looking at an angled force, you're pretty much always going to have to find force normal before you can find your actual answer, because force normal shows up in the x and y directions because of that friction equation. So that's what we're going to have to do here. We're going to have to look at the y direction to get another equation so that we can actually solve for force normal. Then we can go ahead and solve for pull. And as you'll find out, we don't actually need to solve for force normal. We're just going to use force normal as like a mathematical tool in our quest to solve for pull. Hopefully that makes a little more sense here on the next couple of slides. Okay, so we're still chugging along. In that last slide, we got an equation that involved force normal. It involved pull, cosine. It was our x direction equation. We call it a balance because it's showing how the forces are in balance. That's actually an engineering term I kind of borrowed. It's not necessarily a physics term. So now let's do the y direction balance. Let's look at those forces in the y direction. And in this case, balance actually is the correct term, because when we look at our Newton's second law there, F equals ma, looking at the y direction now, and again, x and y are completely separate problems. So in step 2, we looked at the x direction, we ignored y. Here in step 3, it's time to look at the y direction. We're going to ignore x, no x direction. And then the last step, step 4, is where we combine the x and y directions together. So for step 3 here, ignore x, just like we ignored y in the last step. So here in the y direction, there is no acceleration, right? It told that to us in the problem, but we could also figure that out using a little bit of common sense. So acceleration y is 0 because the box isn't moving up or down, right? The x direction is here. We have our y direction, excuse me. We're not talking, again, I said ignore x direction. X direction doesn't exist. We're in the y direction. The y direction, pretend I could draw a straight line, is up and it's down. It's not left or right. So this box is going, as it says right here, I'm not going to draw another arrow because I've already got a good arrow there. It's going to the right. It's completely accelerating in the x direction. It's not accelerating in the y direction, right? If it was accelerating in the y direction, that means it's magically floating, or it's falling through the ground, or something like that. This box isn't moving up or down, so it has no acceleration in the y direction. So that's back to what we're used to, back to what we like, 0. It's all nice and balanced. Everything that's all of our up forces are balanced out by our down forces. So when we look visually at the diagram over here on the left, if we look over here, I'm going to kind of be like, hey, look over here. Okay, if we look over there, we can see that visually. Before we even look mathematically, let's just think about it logically here. Our up and our down, they balance out. So our up forces are normal and pull y, right? Because this pull is actually pulling it upwards slightly. So that normal force plus that strength of the pull y have to balance out with weight. So if we add normal force and pull y together, I'm going to do that here visually. If we add normal force and pull y together, this upwards team here of forces in action are going to balance out against weight. They're going to be equal to weight down here on the bottom. So those two forces together up here balance out weight down here. So now let's do the numbers. We've kind of thought it through logically. Let's do the math. So use the XY diagram to fill in forces for F net Y. Boom, there we go. Just like we talked about our positive forces in the Y direction, we've got our two positive forces down here. We've got pull Y and force normal in the positive direction. We've got weight in the negative direction as shown by the negative sign. We subtract that one because it's negative. And whoops, that works. I wasn't quite ready for that, but that's okay. And that's equal to 0, right? 0. That's still Newton's second law. We've got F net over here with our three forces. We've got mass times acceleration on the right, which is 0. So let's go ahead and move weight to the other side because that 0 isn't particularly helpful. So if we get rid of that negative sign, we're just going to add weight to both sides. And that shows us what we just talked about over there, right? We just talked about that visually. Now we see it mathematically. That pull y and normal force added together, that equals weight. That balances out. So we've got that visually. We've got that mathematically. And remember, the goal here was to solve for force normal. Once we solve for force normal, we can solve for force pull. So again, we've got the tools we need. We've got a force normal, got a force pull, so we're headed in the right direction. So let's solve for force normal there, and I'm going to go ahead and get this red line out of our way so it's not bugging us. Solving for force normal there, I just subtracted pull y from both sides. So I moved pull y over to the right with some subtraction. So force normal is equal to the force of weight, the force of gravity, minus the strength of pull in the y direction. So we need to figure out, okay, how do we get that pull in the y direction? Just like we got pull in the x direction with cosine, we're going to get pull in the y direction, well, with sine. I kind of a little spoiler alert there. Whoops. Okay, I meant to pause here and let you think about it for a minute, but I'm not going to go back and re-record all of that. So let's think about why is pull y sine. That we can think about. So why was it sine? Just a good little hint to save yourself some time, though. If you've already figured out that one direction is cosine, if x is cosine, y is going to be sine. That's how triangles work. They only have three sides. The hypotenuse is off limits, so the other ones are either x or y. So if sine is one, cosine is the other. Process of elimination. We know it's sine. Let's figure out why it's sine. If you look at the triangle here, you can see that y way over here is very far away from our 30-degree angle over here. It's not touching it at all. That makes it opposite. That's the so part. S is for sine. O is for opposite. That's what this is going to show. Opposite, sine. So SOHCAHTOA, and we don't even need the TOA part. Ignore the TOA part. We don't use tangent in this class. So you can just ignore that TOA part. But SOH, reminds you that sine goes with opposite and hypotenuse. CAH, reminds you that cosine goes with adjacent and hypotenuse. So since y is opposite over here, that tells us we want sine. We already knew we wanted sine because the other one was cosine, but it's always good to double check. So pull y becomes pull times sine of 30 degrees, which is our angle. So again, pull y isn't really a real force. Pull y isn't a real force. It's just the representation of that angled pull force in the y direction. So at some point when you have an x portion or a y portion like this, like we had with, pole y here, please, like we had with pole y, we're going to have to go back to the real world at some point and turn that into regular old pole. And that's where the sines and cosines come in. So that's what we just did. We had pole y, which was very helpful to set up our problem. Thank you, pole y. But it's time to put pole y away now and go back to regular pole, because that's what we actually want for this problem. That's our goal. Our goal here this whole time has been pole. And so pole y doesn't help us anymore. We got to get back to pole. How do we do that? We did that with sine. We did that with some trigonometry, looking at sine. Is it sine? Is it cosine? In the y direction, in this case, it's sine. So here's the equation that's actually useful. Is we've got that the normal force is equal to the force of gravity, which is mass times gravity, always mass times gravity, and on Earth G is 9.8, and then minus pole times sine 30. So normal force equals mg minus pole sine 30. We did a lot of math to get there, but in the end, it's all just this Newton's second law equation, right? You've come a long way. We've started here. F net in the y direction equals mass times acceleration in the y direction, or even more simple, F net in the y direction equals 0. Right? We got all this from 0. We started at 0 here, and now we've got all of this great information about force normal. But again, we've got one equation, and there's two things we don't know. We still don't know two things. We don't know pole, and we still don't know force normal. It looks like we do, but we don't, because we don't know pole. So we still can't exactly solve for force normal. But here's the thing. We have two equations now, right? We have the equation from step 2, the x direction equation. We have this new equation from step 3, the y direction equation. We have two equations. There's two things we don't know. We can solve for that. As long as there's an equation for everything you don't know, you can solve for that. It's not easy. It's hard enough with only one equation. It becomes harder now with two equations. You can do it with 3, 4, 5 equations even. It just gets harder and harder and harder. At some point, you need a computer to do it for you. That's one thing spreadsheets can do, is they can calculate hundreds of equations all with a click of a button. They're very, very useful for that. Right now, we just have two, fortunately. We have two equations. We had our x direction equation from step 2. We have our new y direction equation here from step 3. We need to combine them, have them work together to solve for pole, to solve for what we don't know. That's the next step. I'm going to go ahead and erase this circle here so we can read what just popped up. So what just popped up? I just plugged in our numbers, right? We know m, it's 62 kilograms. We know g, because we're on Earth, 9.8. So I just plugged that in. That's all I did there, is I just plugged in some actual numbers. And now we need to combine the equations. That's what that last part says, is we take our force normal from this equation and we plug it into our force normal from the other equation, and all the pieces kind of fit together. I'll show you that here on the next slide. So I know this has been a lot. That's for sure. This is a beast of a problem. Like I said, hardest problem of the semester. So if you're feeling a little overwhelmed, don't worry. Like, that's very normal. Of course, we're gonna do another practice problem like this before the quiz, and then on the quiz, I'm gonna make sure that it looks exactly, well, maybe not exactly, but the problem's going to be very different. Maybe it's not some guy dragging a box, but by the time you get to the point where you're drawing your XY diagram, it's going to pretty much look exactly like this. Or maybe it'll look like the lawnmower one, where pull Y or push Y or whatever is going down instead of up. But it'll look exactly like a problem we've done before, and I'll break it up into several steps. So just like this PowerPoint was broken up into 4 steps to solve the problem, that problem on the quiz will be broken up into at least 4 parts, maybe even more, so that if you can't remember how to do all of this, you'll still get plenty of credit for the parts you do remember. Again, that just reminds you of how important it is to show your work. There's a lot of physics thinking, so even if you make a mathematical mistake, which is really what most of this is, the physics comes from setting up your force equations and maybe a little bit from the sines and cosines, recognizing your triangles. That's really the physics. And the rest of this is algebra. So if you set up your physics correctly and make an algebra mistake, I'm still going to give you the majority of the points. Unless you don't show me your work, then I can't give you credit for things I can't see. So please show your work, especially since I'm not there to actually see it, work with you on it. I need you guys to show me what's going on, so that I can see your thinking, if there's anything I need to help you correct or give you partial credit for, anything like that. So anyway, in our last step, we got a y direction equation that helped us solve for force normal, and the step before that, we got an x direction equation. So there it was. There was our x direction equation from way back in step 2. And the nice thing about when you're doing these problems is you can work on paper, so you can see what you're doing the whole time. That x direction equation had vanished from us here for a little while. It's been probably 10 minutes since we've seen that thing. But there it is, back from step 2, our x direction equation. And then the y direction equation we just solved for in step 3. So what do we do with those? Just like the arrow shows, it's like a giant mathematical turducken. You take the y direction equation and you jam it right into the x direction equation. If you don't know a turducken, I don't even know if it's a real thing, to be perfectly honest, but it's where you take like a turkey and you jam it inside a duck, and then you stick it inside a chicken, I think is how it works. So that's what reference I'm trying to make here is you take this force normal here, that'll be like our duck, and we need to plug it into this x direction equation here. That'll be like our chicken. So we're like stuffing the chicken here. We're stuffing the equation, and as you can imagine, right, when you have all those birds stuffed inside each other, it looks like a giant mess. And that's exactly what this looks like, right? A giant mess. There's a giant mess there, but if you take a deep breath, you'll see where it all came from. You'll see where that all came from. So let's start. Ignore that giant mess of numbers at the bottom right now, please. Just look up here at x direction equation. That's scary enough. We don't need to worry about that stuff down there quite yet. The x direction equation, you see all the pieces are there. We have pole times cosine 30 minus mu times force normal equals 24.8 newtons. Okay, are you ready? Let's look down here. Let's look at the giant messy equation. Look down here, you'll see all the pieces are there. It's the same pieces. We still have pole cosine 30, right? Pole cosine 30 is still there. That hasn't changed. That's still our friend. We still have pole cosine 30. We still have mu. Let's find a color I haven't used yet. Yellow, actually. We haven't used the plain old yellow. We still have mu. Mu hasn't changed at all. That's still our friend. And we still have force normal. It just looks a little different. It just got fat. But it's still force normal, right? That hasn't changed. That just comes from right here, our y direction equation. This whole big thing, 62 kilograms times 9.8 meters per second squared minus pole sine 30. That whole big thing is just force normal. That's what y direction equation says. It says force normal equals that. So we just took that and we jammed it into our force normal. So now everything's in one equation, and let's look at that, right? Remember I said you can only solve things one at a time. One equation can only solve for one thing. The problem with our x direction equation is that it's just one equation that has two unknowns. We didn't know pole, we didn't know force normal, right? We know mu, it told us mu in the problem, 0.48, so that's not an unknown, that's not an issue. The issue was pole and force normal. We didn't know those things. We only had one equation, we had two unknowns, can't do it. Same thing with y. Y had force normal, y had pole, couldn't do it. One equation, two things we didn't know. This giant messy equation down here at the bottom, I mean, we hate it because it's a giant mess. We know it's going to be hard, and it is, but we can do it. But this giant messy equation down here at the bottom just has pull, and it has pull again, but it doesn't have anything else. The only thing we don't know down here in this messy equation is pull. One equation, one thing we don't know, we can do that. We can solve this equation. So why did we do all of this work? We did it for this. We did it to get here. I'm going to erase this giant circles because I know it'll be in our way. But we did all of that to get to this point. Now we can solve for pull. We've got an equation we can use to solve for pull. It's ugly. We hate it. We already hate it. We can use it. So let's do that. Let's walk it through one step at a time. The first step is to get some actual numbers in there, right? Sine and cosine, we hate that. So let's figure out what those things are. Cosine of 30 degrees, calculator, Google. Since you're at home, honestly, I recommend using Google. Like calculators, they're a bit outdated, personally. They can do some incredible things. With a good graphing calculator, you can figure out some incredible things. That is a great tool. But to be perfectly honest, there's nothing your basic calculator can do that Google can't do. So just pop open a Google browser and type in cosine 30 degrees, and it'll give you 0.87. Sine of 30 degrees happens to be a perfect even 0.5, and that's not even rounded. It is exactly 0.5. That's nice. And mu, our coefficient of friction, was 0.8. Let's go in order. I'm kind of rambling here because I'm getting a little excited, but let's see. Cosine 30, right here, cosine 30, 0.87. Mu, right here, 0.48. When you take 62 times 9.8, that gives you 607.6. So I just multiplied those two numbers together. Then we've got sine of 30 here is 0.5, and then 24.8 is still 24.8. That hasn't changed. We didn't do anything to 24.8. Oof, that looks nicer, right? Still got a lot going on down there, but it's starting to look doable. We just made it look a lot prettier down there. So the next step is to do something called combining like terms. Or wait, no, sorry, we've got a distributive property. Distributive property first. This is why I don't teach math, because I do so much math in my head that I kind of forget to explain it all, and I just jump to the end. So first we have to do distributive property. We've got to multiply that 0.48 by everything in the brackets. That's all of this stuff right here. All of this stuff has to be multiplied over here by this 0.48. So that's called the distributive property in math. We take the 0.48, we multiply it by 607.6, and we multiply it here by this negative pull times 0.5. That is a very common mistake in this problem. People forget this negative here. You got to distribute that as well. I actually very clearly remember I myself, the first time I made the answer key for this problem, I forgot to do that. I forgot the negative, got it wrong. So don't forget your negatives. So that's the first thing I did. So we have the first thing we have is 0.87 times pull. I'm getting a little happy here with these lines. I'm going to stop with the lines. 0.87 times pull is that first thing we have. That hasn't changed. I rearranged it around a little bit, but has still the same thing. 0.48 times 607.6. And again, that's something I forgot as well. I'm glad I noticed it when I made this answer key. I was like, that negative, where did that negative come from? Right here, there's another negative hiding in this. That 0.48 itself is negative. That's why I said, remember way back at the beginning of the year, there's no such thing as subtraction. You're just adding a negative. This is why I said that. This problem right here, because I forget that thing every time. That negative in front of the 0.48. So the 0.48 itself is negative as well. I'm glad I caught that. So, well, I didn't catch it. The PowerPoint did. I'm glad last year me caught that. Good job. So Negative 0.48 times 607.6 is equal to, down here, equal to negative 291.6 newtons. And then negative 0.48 times negative 0.5 pull gives us 0.24 pull, which you can see makes sense, right? 0.48 times 1/2, 0.48 divided by 2 is 0.24. I've been rambling. Deep breath for a second. What did we just do? We took this negative, almost made the same mistake again. I'm going to go back, I'm going to get it right. What did we just do? We took this negative 0.48 right here, and we multiplied it by this term right here, and that gave us this equation right here. Again, at this point, we're very, very far in to what would be at least a 4-part problem on a quiz. So if you get to this point and you're just like, the math is overwhelming me, you're probably already getting an 8, 8.5 out of 10 on the problem. So don't kill yourself over this last little bit. For those of us in here who really love math, you can go all the way and get this problem fully answered here, because we're almost done. So we've got this nice clean problem at the bottom here. Let's go ahead and now we're going to do what's called combining like terms. We've got 2 things down there with pull in them. We need to add those together to make one thing with pull in it, and that will leave us with the newtons. Right? We have 2 things down there that have newtons in them without any unknowns, no variables, they're just numbers, right? We've got a negative 291.6. On the other side, on the right side of the equation, we've got a 24.8. And then we have the 2 terms that have pull. We have the 0.87 pull, and we have the 0.24 pull. So first, let's add the pulls together, right? 0.87 pull plus 0.24 pull gives us 1.11 pull. I just added the 0.87 and the 0.24 to get 1.11. Now let's go ahead and move the 291.6 to the other side through addition, right? So we've got a negative 291.6 newtons. How do we get rid of a negative 291.6 newtons? By adding a 291.6 newtons. So let's add 291.6 newtons to both sides. When you do that, you get 316.4 newtons on the other side. So 24.8 plus 291.6 gives you 316.4. Now, to get pull by itself, you just divide by 1.11, right? So how do you undo a 1.11 times pull? You got to divide by 1.11. And that's it. Finally. Holy cow. It doesn't even feel like, it should be over at that point, right? Like, where are the fireworks and all that after all this? You feel like there should be some like music at the end of the video game at least or something, but nope. All you get is a nice bolded 285 newtons. Maybe I'll try to like draw a smiley face. You get Mr. Simon's terrible artwork with his right hand mouse. Maybe like a gold star. I don't even think that's gold. I think it's yellow. Oh, this might be gold. Hey, I like that. There you go. You get a gold star and a smiley face. But that's it. That's the answer. All joking aside, 285 newtons is the answer. So how did we get here? It's been a long way, right? It's been a 45-minute journey to get here. Pain in the butt, but we did it. The hardest problem of the year. We started with the diagram, right? We started with this stuff over here. The free body diagram and the XY diagram. That got us all organized. Boom, right there, 2 points on the quiz, just for drawing those arrows and labeling them. So we can all do that. Step 2 was to do F equals MA in the X direction, and even just for writing F equals MA, that's going to be worth at least half a point. I'm trying to tell you guys here how to get 1 point at a time, and then if you're able to get all the way to the end and get all the points, awesome. If not, at least you're getting a B, A minus. So if you're going into a STEM field, Trust me, I learned the hard way with a C- in organic chemistry. Just take every point you can get. So that was step 2. You've got the x direction balance, the F equals ma in the x direction using our x direction forces, right? Pull x and friction, and keeping in mind that there was an acceleration in the x direction as well. So F equals ma in the x direction right here. That was step 2. Step 3 was right here, doing that same thing in the y direction and getting an equation from that. And we looked at our y direction forces. And then step 4 was to put them together. We plugged our y into our x, made a giant mess of things that we used our algebra skills to sort out. So if you get to this point right here, if you're able to get to that point where you substitute for force normal, where you're attempting at least to jam this one force normal into the other, maybe you're not successful, but at least I can see what you're going for. You're probably, like I said, getting at least 8 out of 10, maybe even more. And then if you're successful with all of that terrible math and you get down to that 285 at the bottom, nice 10 out of 10. So don't be super discouraged if that math at the bottom isn't making sense to you. If the sine and cosines are making sense to you, if it makes sense to split up the x and the y, that each direction the x gets its own F equals ma, and the y then also gets its own F equals ma. You don't put them together till the very, very end. If all of that makes sense to you, you're going to be just fine. And then if you're a math person, I know some of us are math people, some of us aren't, but if you're a math person and you watched this here at the end and that all made sense to you, or maybe you looked at the answer key, because remember, like I said, the answer key that I sent you guys yesterday or today, if you didn't get your homework done yesterday, that answer key has a slightly different. Overall, it's still the same. In the end, you find a force normal and you plug it into a different force normal. But I did some substituting and plugging things along in there a little bit differently. So if this didn't quite make sense to you, at least look at the answer key. Maybe that'll be better, and we will be just fine. So make sure you answer your exit ticket from today. As always, it's just a reflection. How are you feeling about this? How are you feeling about this concept in general? Problems 1, 2, and 3 from the homework, were those ones okay? Maybe this one was way hard and that's fine, but if you're doing okay with problems 1, 2, and 3 with just the basics of using sine and cosine to get your x and y, if that is doing all right, then you are in good shape. If you're still struggling with where to use sine and where to use cosine, please send me a chat message. I've done a few video calls successfully to help a few people, so I'm starting to feel good about that. We could do a video chat. I'm going to really try, I think Friday, maybe we can do Fridays or Thursdays. We'll figure something out, but a weekly time where I'll host a meeting, just a meeting in the Teams channel that anyone can join and ask me questions, and I can help you guys out. So make sure you do your exit ticket, get your points for the day, and I'll see you next time on Mr. Simon's YouTube channel.